Start recording. There we go. We've been talking about graph theory. Let's go over a few special types of graphs. First, we have cycles. Cycles are where you have a sequence of vertices that are connected in a loop, and that's all. There's like no other edges, just a sequence of vertices that sort of form a circle, or the closest you can get to a circle with that many vertices, like a polygon. So the smallest cycle you can make is 3 vertices, because you can't make a cycle on 2 vertices. You could, do that, but that's multi-edges, and cycles are actually simple graphs. Actually, all of the types of graphs, all of these special types of graphs I'm going to go over here are specifically types of simple graphs. So a cycle, the next cycle would be 4 vertices, like so. Now, the special notation for a cycle on n vertices, and it is C subscript n. So the smallest cycle is C3. This is C4. Here's a C5. Okay. Now, let's compare cycles to complete graphs. Oops, I spelled complete with a K. There's a reason for that. Complete graphs. The notation for complete graphs is K subscript n, which is why I slipped up there and started spelling complete with a K. But a complete graph on n vertices is basically the sort of maximal simple graph that you could draw. So it has all of the edges. Every vertex is adjacent to every other vertex. So K3 looks like this. You'll notice K3 and C3 happen to be the same. That's fine. But K4 is different from C4, whereas the 4 cycle is just these 4 edges. K4 would be also these 2 edges. Now, it's notable that the way I just drew this graph, there is an intersection of edges right there. It's very important that you understand that just because 2 edges intersect doesn't mean that there's a vertex there, okay? So a lot of times we draw edges so that they are crossing over each other, but with no vertex. So if we were, for example, looking for a path in this, remember I talked about paths and walks and trails. If we were looking for a path in this graph, we could not for example, do something like this. Okay, that would not be a valid move for a path. Okay, because there is no vertex here to arrive at and then leave from. Okay, there's no these edges, this edge and this edge should be considered not touching each other. They're just sort of crossing over each other in a way. I mean, you could actually imagine that this is that these edges are along the edges, like the sharp edges of a oh man, I'm a D&D nerd. I gotta make sure I get my names of solids right. A tetrahedron, there we go. A tetrahedron, which is like a D4. So, in that sense, this one is in front and this one is like in the back, right? So they're not touching each other. Get what I'm saying? You can kind of look at it that way if you imagine that this is in like 3 dimensions, all right? The only vertices are the ones that are notated by the dots. So, and those would be like the sharp points of the tetrahedron. All right. So anyway, Let's draw what K5 looks like. 1, 2, 3, 4, 5 vertices. We've got to go all the way around the outside like that. And then we got to go boop, 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 like that. And so it's, like, looks like you're summoning a demon. It's that nice, what's that called? Pentagram with a circle around it. So in a complete graph, every vertex is adjacent to every other vertex, which means that all of the vertices are of degree n-1. So you'll notice in K3, all of the vertices have degree 2. In K4, all of the vertices have degree 3. And in K5, all of the vertices have degree 4. Okay. While still being a simple graph, so no multi-edges and no loops. And of course, let's put a ... on the end of here, because you can then do like a 6 cycle or a K6 complete graph. You can do it on any finite number of vertices. Okay. And then there's one more special type of graph we want to talk about, which is called a oops, that's not how you spell it, bipartite graph. Bipartite graphs are graphs where vertex set is split into like 2 distinct sets of vertices. You can think of them as different colors, actually, which is a nice way to do it. You've got like the red vertices and the blue vertices. So the vertices are sort of on separate teams, as it were. And the edges that exist in that graph only ever connect vertices from opposite teams, or of different colors, if you will. So the prefix bi in the bipartite, bi means 2. So bipartite basically means like 2 parts. So a bipartite graph specifically has these 2 teams that never have edges between one another. So let's do more examples. So let's do like if you have just 3 vertices like that, then you could have edges like this and like this. That's a bipartite graph. Let's do another one. Let's do like 2 and 2. I'm just doing some examples. I'm not really like going to thoroughly show you all the possible bipartite graphs, but like there's an example of a bipartite graph. Let's do another one. Let's just bump up to like a bunch of them. And then the only edges that we're allowed to have are between the teams, right? Like there, that's an example. That's another, let's do another one like that, maybe. There's another example of a bipartite graph. Okay, you'll notice that we have no connections at all between, no edges that connect red to red, and no edges that connect blue to blue. Okay, etc. These are the 3 like specific types that I want to focus on. Now, for each of these 3 types of graphs, I want to like sort of use each of these to introduce some ideas. So for cycles, I just want to use the concept of a cycle to introduce a new concept called a subgraph. I'm not saying that subgraphs, the concept of a subgraph, is only tied to to cycles. I just want to sort of like use cycles as a segue into talking about subgraphs here. So a subgraph is like a subset of the vertex set with a corresponding subset of the edges set. So it's like a graph within a graph. If you have a large graph with lots of things going on, Let's draw some random large graph. It's not that large, but you know, there's a lot of stuff going on here. There we go. That is a fairly large-ish graph with lots of stuff going on. So now with this graph, I could pick out a subgraph from within it. So let's say I pick 4 vertices, this vertex, this vertex, this vertex, and this vertex. Then I select a subset of the edges that are connecting those vertices. Suppose I select this edge and this edge. That, for example, is a subgraph. Okay. So you have the whole graph, and then you have a subgraph, just a subset of that graph, basically. Okay. This is often when you're looking for subgraphs, like you're looking for particular types of subgraphs. So one of the things you might search for is cycles. If you're looking for subgraphs, you might be interested in whether or not there are any cycles, or otherwise known as cyclic subgraphs within a graph. You might also be looking for complete graphs within a graph. Like, are there any complete subgraphs within the graph? Like a subset of the vertices where are all connected to each other in all possible ways. Let's do a quick example. So another quick example. So let's do that. Let's do 5 vertices. I want to do like this and this. That. Let's give them names: A, B, C, D, E. So in this graph here, you can find a subgraph that looks like C3. There in blue, there is a C3 subgraph. Actually, what I could say is that there is a subgraph that looks like, I'm going to put in parentheses, isomorphic to, because that is a term we have yet to introduce, but when we introduce it, I think that this will make sense. A subgraph that looks like is isomorphic to C3. Okay. You can also find a subgraph in this graph that looks like C4. So if I select these 4 vertices here, there is a subgraph that looks like C4 if I include all of those vertices like that. And then I can even sort of combine them together and make one. I can highlight a particular subgraph here that goes all the way around. You see that? It makes sort of like almost like an M shape in purple there. That would be a subgraph that looks like C5. So here is an example of a graph called G. We can call it G here. And it itself isn't a cycle. It is not C3, nor is it C4, nor is it C5. But it contains subgraphs, not separate subgraphs, not totally distinct, because they use some of the same vertices. But it does contain subgraphs that look like C3, C4, and C5. Okay. So that's the concept of a subgraph. We're going to be talking about subgraphs, and like the concept of a subgraph is used in various theorems and strategies and proofs that we'll be introducing soon. Okay. How are we doing? Any questions?
How do you know if you got all the subgraphs?
Oh, yeah, great question. Like, the set of all subgraphs is kind of like the idea, it's kind of like a power set. It's like the set of all subsets of a set, you know? There could be lots of them. So that wasn't all of the subgraphs by any means. That was just 3 examples, right? If you wanted to define the set of all subgraphs of a graph, you could certainly do that. And then you'd have to go through and talk about all of the subgraphs with one vertex, which is basically just each individual vertex taken one at a time. And then you like all of the subgraphs with 2 vertices. And then you've got the question of like whether those vertices are connected with an edge or not. And then all of the subgraphs of 3 vertices. And again, how many different edges are you going to include? You could include 1, 2, or 3 edges. And like there will be a lot of them. Does that make sense?
Yeah, sounds pretty mechanical.
Yeah, it would definitely be well, let me take this opportunity to say that a lot of graph algorithms are complicated. And it is not uncommon to have graph algorithms that are like exponential in their like time efficiency. On the topic of P and NP, which I know some of you are going to be studying, graph algorithms, not all of them by any means, but many graph algorithms are like in the NP category, okay? Because like solving graph problems often involves like checking subgraphs and paths and things, and because of the nature of networks of being sort of like they get more and more complicated very quickly as you go up. As you increase the number of vertices, it's like their complexity increases exponentially with the number of vertices. So it's just kind of inherent in the nature of graphs and trees and things. Trees less so, but graphs for sure. Yeah, I'll just say that. Like I said, not all graph algorithms are in NP. So there's some that are decidedly in P, which is great. But graph theory is one of those places, one of those areas of mathematics where like there are algorithms, but they're not necessarily efficient. Okay. So, all right. Let's talk about complete graphs. Yesterday, you guys were exploring the question of how many edges are in KN. And you guys guessed, let's call this a conjecture. Let's use a nice word. A few of you conjectured. I believe this was Ben's conjecture initially, but then we had some of you concurred, and that gained support. And we tested it a few times, and it seemed to work. The guess is n squared minus n over 2, right? So did anybody check it with like 6 vertices? Six, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think the answer is 15 edges. And if you do 6 squared minus 6 all over 2, you get 30 over 2, which is indeed 15. Yep. So that worked, right? So yeah, it works with that. So that's seeming pretty promising, right? So why you guys had an approach to explaining like why this is the answer. I think you guys said it was like n minus 1 plus n minus 2 plus n minus 3 plus ... all the way down to 1, right? And that was kind of the idea of like you're gonna put for one of the vertices, you're gonna put n minus 1 edges, and then for the next vertex you've already got 1, so you're going to do n minus 2, and then for the next vertex after that you've already got 2, so you only need to do n minus 3, and then for the next vertex you only need to do n minus 2, and then it's only 1 more after that, right? So like it kind of like goes down, it goes the number of new edges you need to add for each vertex as you sort of go around the cycle is just 1 less than the previous time. That's a good proof. I think you guys did a solid job. I give that a seal of approval. I'd say like that is a proof. But I want to propose another way to prove the same fact, because you guys are correct. Your conjecture is correct. But another approach to that proof is to use a counting strategy. N choose 2. N choose 2. What is an edge? An edge is a connection between exactly 2 vertices, 2 distinct vertices. Distinct because we're talking about a simple graph, so no loops. And no multi-edges, so we can only have up to 1 edge between any 2 specific distinct vertices. So what are the total number of possible vertices you can have? It's just the total number of different ways that you can choose 2 vertices from a set of n vertices. So n choose 2 is the answer. That's a counting approach. And n choose 2 happens to be calculated n factorial over 2 factorial times n minus 2 factorial. And what is this reduced to? N factorial over n minus 2 factorial. That reduces to n times n minus 1, because the n minus 2 factorial cancels out. And then you get exactly the formula that you all came up with. So there's 2 different approaches to proving the same fact, which is that the number of edges in a complete graph on n vertices is n choose 2, which basically means like, is if you're sticking to simple graphs only, you can never have more than that many edges. It's a limit on the number of edges that can exist, right? Because there's only so many different possible edges you can put on a finite number of vertices and still have it be simple. No loops, no multi-edges. So what's the lower bound? If that's an upper bound, maximum number of edges, what's the minimum number of edges?
N?
N? Why N?
Let me rephrase. It could be 0, depending on how you rule it. Assuming everything needs a connection, it is N. Otherwise, it could be any number from N to 0.
Good. So almost. You're off a little bit on that. I believe it should be n minus 1.
3-vertex triangle requires 3 lines to connect.
I believe it should be n minus 1. Oh no, is it n?
It's unless I'm miscounting, it is N.
Okay, so you could make you don't have to make a cycle. You could also put 1 vertex in the middle and just put edges out to all the other ones. I think is n minus 1. But that's assuming that you would need it to be connected, which we don't. So the concept of connectivity, like whether the graph is fully connected or whether there are separate connected components, that's the topic of actually the next section, 10.4. So in general, if you don't make any restrictions on connectivity, the minimum number of edges is 0. You can just have a graph with a bunch of vertices and no edges. That's okay. So just bear that in mind. That's kind of a trick question. I think I asked it because I wanted to bring up the concept of connectivity and point out that like graphs don't have to be connected. Okay. So anyway, so we have that. Now, for the bipartite graphs, we have a little more we can learn about bipartite graphs. Question: is this graph bipartite? Okay, is that a bipartite graph or not? How could you tell?
I don't think it is.
No?
No.
We have a couple of votes for yes in the chat. We have another vote for no. So far, it's 2-2. Anyone else want to vote?
I'm going to go for no.
Oh, another vote for no. Ooh. So this is a question we might want to ask. Okay, so I don't know a lot about the applications of bipartite graphs, but just abstractly, let's suppose you wanted to take a graph and identify, is it bipartite or not? Well, one approach to answering that question is to recall that, like, the concept of a bipartite graph is that there are two teams, right? It's a bipartition of the vertices, and there are no edges within vertices that are on the same team, right? So what you could do is look at your graph and just say, let's start assigning teams, right? That doesn't really matter which is the red team and which is the blue team, or how you want to do the team. You could label them 1 or 2. It doesn't really matter. I'm going to label them red and blue. So let's say that this vertex is red. I just made that decision totally arbitrarily, because I don't know. I just thought that would be, yeah, just there's a random vertex. Let's say that one's on the red team. So now that one's on the red team, any vertex adjacent to that vertex has to be on the blue team, right? Because the rule for a bipartite graph is that none of the red vertices can be adjacent to one another. They can only be adjacent to blue vertices. So anything adjacent to this vertex has to be blue. So this one's got to be blue, and this one's got to be blue, and this one's got to be blue, and this one's got to be blue. All right. Now, is this bipartite? I think we're getting lots of no's with more confidence now. What makes you more confident now than you were before?
There are 2 blue vertices connected to each other when there can't be, which violates the rules.
Perfect. Violates the bipartite rule. That's correct. So we can say this is not bipartite. So what I just demonstrated there is the value and the power of what's called graph coloring, right? It is, hey, let's start assigning colors to the vertices. And if we do it in such a way that we follow the rule that no 2 adjacent vertices can be the same color, then can we do that? Or do we encounter some contradiction like we did here? Here we contradicted that rule right away. So this graph is, we would say this graph is not 2 colorable. When you're talking about graph coloring, we always follow that rule that adjacent vertices cannot be the same color. So it is not possible to color the vertices of this graph with only 2 colors. It would require more than 2. So it is not 2 colorable. And the concept of a graph being 2 colorable is in fact synonymous with it being bipartite. So bipartite graph is a 2 colorable graph, if and only if. So that is one approach to like, how can you check to see if a graph is bipartite or not? Well, try to do a 2 coloring of that graph, right? Try to color it following the traditional coloring rules of adjacent vertices have to be different. with just two colors. And if you can do it, it's bipartite. If you can't do it, it's not bipartite. There we go. But let's dig into this a little bit deeper to explore exactly why it is. Why was this graph not bipartite, not two colorable? What was it about this that made it not two colorable? You'll notice we had this configuration of a triangle. A triangle will never be two colorable. So this is a C3 subgraph, right? A subgraph which looks like a cycle on 3 vertices. By the way, you'll notice that I just realized I haven't been labeling vertices at all, because for the topic of this discussion, like, we don't really care what the vertices are named. This is really about the structure and less about the details of like what the vertices are called or what they represent or whatever. So yeah, I haven't been bothering to name any vertices. So when I say this is like isomorphic to C3, because I never even labeled them, we might as well just say it is C3, whatever. So that, what do I want to say? Yeah, that triangle there, that's kind of why it couldn't be colored with two colors, right? Same with there's another triangle over here as well. Yeah. Let's look at another example though. Let's look at the K5. Oh, or no, let's just look at C5. Is C5 two colorable? So is this bipartite? In other words, is this two colorable? Should the same question. It is not. That's right, because let's see what happens. If I assign one red, the adjacent vertices have to be blue. The adjacent vertices to those have to be red, and oops, there's our contradiction. So, no. Okay. So it's not just triangles. In fact, you might be able to tell that anytime you have a cycle of an odd number of vertices, it's not going to be possible to do a two coloring of that graph. And if the graph had some other things going on, say the graph had other stuff, here's some more vertices, whatever, say these are doing things, if this was a part of a larger network of things, okay, like let's suppose the graph just kind of continues outwards and it's large, and this is just a small part of it. The very fact that the larger graph contains this copy of C5 right here, that fact alone is going to tell you that the entire graph is not two colorable and therefore not bipartite. And so this is a theorem about bipartite graphs. A graph G is bipartite if and only if it does not contain an odd cycle subgraph. So basically, if it does not contain a subgraph isomorphic to an odd cycle, as long as it doesn't have an odd cycle, then it will be two colorable and it will be bipartite. But if it's not bipartite, it will necessarily have an odd cycle in it somewhere. Okay, so that turns out to be an if and only if. I won't go through the whole proof, but it's a nice condition that you can check and sort of connect to the concept of being bipartite. Okay, so this is cool because it kind of ties together a few different things. ties together the concept of a bipartite graph with the concept of graph coloring, and also the concept of subgraph containment and cyclic subgraph containment in particular. Okay. So this has all been just, introduction to more concepts in graph theory, and this is all sort of precursor to the main thing I wanted to start talking about today, which is the idea of graph isomorphism. It's a word I've been tossing about without really telling you what it means, but now I'll tell you. Okay. Here's two graphs. Let's call them G1 and G2. Let's say this is A, B. Oh, hang on. How did I label this? Oh, yeah. A, B, C, and D. And then this one is A, B, C, and D with capital letters. Okay, so we have graph 1 and graph 2. Are these graphs the same? What does the same even mean for graphs? Okay, so are these graphs the same? We have a vote for no. Oh, they are similar, but no, they're not the same. Why aren't they the same?
I think those are isomorphic.
They are isomorphic. We haven't gotten to that yet, but they're not the same. And by the same, I mean equal.
Okay, so you're saying in ordering they have to be the same?
Well, for one thing, they have different vertex sets. Maybe this wasn't quite clear, but I did intend for the lowercase letters to be different from the uppercase letters. Right? That's not the same as capital A, B, C, D. Right? For one thing, they have different vertex sets. But even if we consider them to be the same vertex sets, like even if the lowercase letter a is the same as the capital letter A, they are like arranged differently, right? So these two graphs are not equal, right? Because in order for two graphs to be equal, they have to have the exact same vertex set and the exact same edge set. So yeah, Nicholas is paying attention to the degrees. So like, yeah, I love what Nicholas said there, and Ibrahim as well, paying attention to like which vertices are adjacent in one and which. So yeah, so there's two things going on there. Ibrahim says A and B are adjacent here, but A and B are not adjacent here, so that makes them different. Nicholas says D has degree 1 in this graph, but D has degree 3 in that graph. So again, not the same. So they are different graphs, but they are what we call isomorphic. So isomorphic is a different, so sort of a different way of defining sameness. And the symbol for isomorphism is like an equal sign with a squiggle above it, like an equal sign with a tilde on top of it. So it's sort of like a triple equal sign, except the very top one is, yeah. So that is this sort of isomorphic symbol. And what isomorphic means, okay, so in casual terms, what isomorphic means is that you can rearrange one of the graphs without breaking anything or removing or adding anything. You can rearrange it so that it looks exactly like the other one. And then maybe you could just relabel it. But some relabeling of the vertices would make it identical to the other one. So that is the concept of isomorphism. It's like the isomorphism is, two graphs are isomorphic is if they basically have the same exact shape. Maybe they're arranged in a different configuration, but they are the same shape with the same structure. And as for labeling, it doesn't matter. That's isomorphism. The way we define it is that G1 is isomorphic to G2 if and only if there exists a bijective function, a bijection f from the vertex set of G1 to the vertex set of G2. So there's a bijection between the vertex sets that preserves adjacency, which what preserves adjacency means is that like A is adjacent to B in the first graph, G1, if and only if F of A is adjacent to F of B in the second graph. Okay, so and that's an if and only if, which means it goes both ways. Okay, it's like if A and B are adjacent in graph 1, then the images of those vertices under this bijection that you're mapping, so where they're mapping them to, those image vertices in G2 are also adjacent, and vice versa. The adjacencies, you only have adjacencies in the images F of A and F of B. If you ever do, then the original vertices would have had to be adjacent as well. So that's this concept of preserves adjacency. Okay, so in this example, we could look and at the structure, and we could figure out how to map them. We could say, all right, this vertex D has to be associated with this vertex A, right? Because in G1, D is the only vertex of degree 1. And in G2, A is the only vertex of degree 1. So we have to connect those. And then the vertex which is adjacent to D has to map to the vertex which is adjacent to A. So those two have to be associated with in our bijection. And then the other two can be whatever. The other two can kind of, it doesn't matter. If we map A to B and C to C, that would work fine. Or alternatively, we could map A to C and then C to B, and that would work fine as well, because it's sort of symmetrical. So let's define, let's prove that G1 and G2 are isomorphic. We start by defining F from the vertex set of G1 to the vertex set of G2. So we'll call that V1 to V2. And I'm going to define that just like this. So I'm just going to define it with an arrow diagram. I said I was going to map D, lowercase d, to capital A. So that would be that map, that mapping. So F of D equals capital A. We're going to map lowercase b to capital D, like that. So F of lowercase b equals capital D. And then the other two can be whatever. So I'm just going to map A to capital B and C to capital C, like that. There we go. So that is my bijection right there. And I didn't even, you notice, I just, since these are both finite sets, you can just draw a diagram and that's sufficient. Okay, so there's our bijection. This is, F is clearly a bijection just because you can tell by looking at it. Remember that the definition of bijection is 1-to-1 and onto. So we have to have the exact same number of vertices in the two graphs. And then when we map them, it's like a 1-to-1 correspondence between the vertex sets. Okay. So that is the bijection, but a bijection alone doesn't prove that the graphs are isomorphic, because obviously you can have two graphs with the same number of vertices and they can look totally different. Like there's one graph and like here's the other graph. And these are not isomorphic to each other, but it would be easy to make a bijection because there's 4 vertices on the left and 4 vertices on the right. So a bijection alone doesn't prove it. There's this very important concept that the bijection, in order to prove isomorphism of graphs, it has to preserve that adjacency. And the mechanism for proving that the F we just defined is to create what are called adjacency matrices for the two graphs, or equivalently adjacency tables. You can kind of arrange it in a table format or a matrix format. I'm just going to do the matrix format. And then just show that those matrices are equal to each other. We're going to save that for another day, so we'll come back to that on Thursday. All right. The last thing I want to show you related to this is just a couple of things on that I posted on D2L. So some handy dandy graph websites. Here's a nice one. On this website, you can sort of construct a graph. Especially if you go into draw mode, it's very easy to. Here we go. It's very easy to add new vertices just by clicking, and then you can click on vertices and add edges all over the place, like that. And then you can like grab them and move them around, right? So here I can nab these vertices and move them places. And so you can rearrange them, which is really nice. And they maintain their adjacencies as you are doing that rearrangement. So this is I don't know how to delete them. Oh, delete. There we go. I delete like that. Got it. Okay. If you're in the force, then it does this cool thing where it kind of just like puts it into a nice simple. It kind of turns it into jelly. They float around, but you can turn that off by being in one of the other modes. Anyway, so that's a useful website for drawing a graph and then rearranging it. And then the other cute website is like a little game you can play where you look at graphs and you say whether they're isomorphic or not. So like, is that graph isomorphic to that graph? Yes, it is. Correct. Continue. Is this graph isomorphic to this graph? Yes or no? Well, that is a triangle with 3 edges, and this is sort of a V shape with only 2 edges. So no. Okay. So that's as far as we'll go today. You can test these out. You can try these websites, and I'll teach you a little more about this concept of isomorphism on Thursday. Have a good one, folks.
Have a good day.
Thanks, Cameron.